limits with the L'Hospital's rule. Limit number 1. Limit as x goes to positive infinity of the difference of two functions. The first one is the square root of x squared plus 3x minus x. We may notice that if x goes to the infinity, the first function goes to the infinity and the second function goes to the infinity, and we do have a difference. Infinity minus infinity is indeterminate form, however, it's not the form ready for applying the L'Hospital rule. We really need to see the form 0 over 0, the quotient form, or infinity over infinity. So now let's try to rewrite this expression and hopefully we can get one of these forms. I will copy my limit as x goes to the positive infinity, x squared plus 3x square root of this minus x, and I will multiply and divide by the conjugate expression, which is x squared plus 3x root plus x, and the same in the denominator. This means I am multiplying and dividing by the conjugate expression. And let's see what we can get. Limit as x goes to positive infinity, I will multiply 1 by x squared plus 3x square root of this plus x in the denominator, and I will distribute everything in the numerator. Foiling conjugate expression, I have to square the first quantity, which the square root is gone, and square the second quantity. Squaring x, I have x squared. Subtraction. I see some simplifications. I can also rewrite my denominator a little bit. I have 3x here. I will factor out x squared, the leading function, from the expression under the square root, and I will have 1 plus 3x over x squared. Okay. And now limit at infinity 3x, and I have x square root of x squared and the square root of 1 plus 3 over x plus x. We may notice that square root of x squared is just x, if x is positive infinity, of course. Okay, that's we do have x 1 plus 3 over x and plus x. Now I see that this is a common factor. Let's factor out. Okay, limit as x goes to positive infinity 3x, factoring out this, I have 1 and the square root of 1 plus 3x plus 1. I can definitely delete this, and I believe I do have nice form that I probably don't even have to apply the L'Hospital rule. 3 over square root of 1 plus 3 over x plus 1. I do have 3, I have 1. 3 over huge number is 0 and 1. That means the final answer is 3. 1 plus 1, 2. 3 halves. That means just using the algebra, I managed to get rid of the indeterminate form and get my final answer. Let's see the second example. Limit number 2. Limit as x goes to positive infinity, x times sine of pi over x. We can see that x is infinity, then this is infinity, pi over huge number is 0. Then I have sine at 0, which is just 0. That's another indeterminate form, the product form. We will try to do the same. We will try to get the form 0 over 0 or infinity over infinity. Then we can apply the L'Hospital rule. limit as x goes to positive infinity. And we remember, having a product, I will flip one of the number. That means sine over pi of x divide by 1 over x instead of multiply by 1 over x. And let's see now. Sine pi over huge number is a small number, 0. Sine at 0, it is 0. And 1 over huge number, 1 over infinity, is also 0. Okay, I do have my form. Limit as x goes to the infinity, sine at pi over x over 1 over x. I can apply the L'Hopital rule because this is definitely 0 over 0. Okay, limit as x goes to the infinity. Derivative of sine of pi over x is cosine of pi over x times derivative of inside function pi over x, which is negative pi over x squared. Derivative of 1 over x is negative 1 over x squared. Yeah, I can work it out. 1 over x, for example, derivative with respect to x means x to the negative 1, negative 1, x to the negative 2, negative 1 over x squared. That means this is derivative basically of the denominator and numerator. Numerator has additional constant pi. Okay. And what I can see some simplification. Limit as x goes, I can put pi in front. I can copy cosine of pi over x. I will have negative 1 over x squared and negative 1 over x squared. I can simplify and I end up with the quantity pi. Cosine pi over huge number is 0. Cosine at 0 is 1. The final answer is pi. We did manage to get the form infinity, 0 over 0, and apply the L'Hopital rule. Okay, and let's see another example. Example number 3. Limit as x goes to positive infinity, e to the power of x minus e to the negative x for x squared. That means, first of all, I see function e to the x on the top, and I see function x squared. We know that exponential function grows much, much faster. That means talking about the growing rates at infinity, numerator is growing faster. Always infinity. Always. That means just based on this relation between the leading functions from the numerator and denominator, I know that numerator is winning always, then always infinity. But let's apply the L'Hopital rule. Because what we have, if x is infinity, e to the x at infinity is infinity, and quadratic function at infinity is infinity. I think I can apply the L'Hopital rule right away. Let's see. Derivative. Derivative of e to the x, e to the x. Derivative of e to the negative x, e to the negative x times negative. And both negatives will give me positive. In the denominator, 8x. And I believe I have another infinity over infinity. We will apply the L'Hopital rule the second time. H. Limit at infinity. Derivative of e to the x, e to the x. Derivative of e to the negative x, e to the negative x times negative. And 8. 8x is 8. Okay. And what we have now? We do have e to the x, of course, is infinity. E to the negative x at infinity means e at negative infinity, which is 0. That means basically we have something like that, which of course we can't really write this way. It's just a huge number. Infinity minus 0 over 8 is simply infinity. But we know that I do have a reason. It's not based on infinity over infinity. Or you may use right away, you may comparing the growing rates of the function. Okay, and let's solve one more. Number 4, limit as x approaches 0, e to the x plus e to the negative x minus 2, 2x times sine of x. Okay, e to the 0 is 1. E to the 0 is 1. That means we can see we do have 2 minus 2, 0. And sine of 0 is 0, 2 times 0, 0, 0 over 0. I think we can use the L'Hopital rule right away. We can't use the growing rates because this is not limit at infinity. Okay, let's differentiate. Derivative of e to the x, e to the x. Derivative of e to the negative x, negative e to the negative x, and 0. In the denominator, I have to use the product rule. Derivative of 2x is 2 times sine of x plus 2x. Derivative of sine of x is cosine of x. Okay. What we have? Let's check. I have e to the 0 is 1, e to the 0 is 1, which I do have 0. And sine at 0 is 0, cosine at 0 is 1, but it's 2 times x, 2 times 0. Okay, another L'Hopital rule. Let's see. Limit as x goes to positive infinity. Derivative of e to the x, e to the x. E to the negative x is negative e to the x, which will become positive. And then derivative of 2 times sine of x is 2 cosine of x. And another product. Derivative of 2x is 2 times cosine of x plus 2x, derivative of cosine is negative sine of x. Okay, and let's check what we have. Actually, I can use it. E to the 0 is 1, e to the 0 is 1. Excellent, I don't have 0 on the top. 2 times cosine at 0 is actually 1. I can write cosine at 0. Okay, plus 2 times another cosine at 0. Minus 2 times 0, sine at 0 is 0. So my final answer is 2. 2 times 1, 2 times 1, minus 0. 2 times 1, of course, is 2. 2 plus 2 is 4. The final answer is 100.